Uh, so I went and looked through all of the submitted pre-labs, and a lot of people are on it. A few are still a little confused about the basic premise. So let me just review one last time here before we kind of dig deeper. And what is our independent variable for this one?
Frequency.
So one of them is going to be the frequency of our stimulus.
Place on the body.
And the other one is going to be like location on body. Again, location is kind of easy. Location is where, and we're doing it on the calf and we're doing it on the finger. So those are the two specific locations we're going to be able to compare. Frequency, again, what do we mean by frequency of the stimulus?
Like if it's a single pulse of an electrical stimulus or a burst, a bunch of them given in succession.
So in fact, a single pulse wouldn't actually even have a frequency. So frequency means if it's repeating, how quickly is it repeating? Kind of the tempo. If you're a musical kind of person, it would be like the tempo of the stimulus. Sometimes we say cycles per second. Again, if I am looking at my current source here, and I'm like kind of, I've got it on some oscilloscope, I can actually watch it. If I have a single pulse, it would just come out and then that would be done. If I am at 1 hertz though, it would go boom, 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 on and on. Every 1 second, it would have another pulse. So let me make my thing here. This is going to be seconds. 1, 2, 3, 4, 5. If it was 1 hertz, it was every second, it would have another pulse coming out. So 1 hertz, 1 pulse per second. Notice that this is independent of the magnitude. If I'm thinking of the milliamps, this is like the magnitude of the current. Measured in milliamps. I could have something that has twice as many milliamps, but still be 1 hertz, right? So the magnitude in milliamps is a separate parameter from the frequency. The frequency is the speed of repetition, the tempo. The BPM, if you're like kind of going, you're like little, DJ mixing up your dance beats, you're like, how many beats per minute does this have? That beats per minute is hertz. No, actually it's not hertz, it's hertz times 60. Right, because hertz is per second. So it's like BPS, beats per second. So this is something a few people got confused though. The idea, magnitude of the stimulus, how many milliamps, how strong is the current versus how fast is it repeating, are these pulses repeating? So keep those separate when you are thinking about this, because otherwise you'll get confused. Right, I could have something that's twice as fast. 2 hertz would be boom, do, 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 do. It's like 2 every second. I could have the same magnitude, but have twice the frequency. It's the same number of milliamps, but it's the pulses are coming out twice as fast. So does that make sense? I really want, please, if anybody is still confused about what is Hertz measuring versus what is this magnitude in milliamps measuring, please ask now, because otherwise it's going to be confusing. This is weird. You can see let me turn off this video here because it's freaky to see my chin here. Oh. So it's all clear, crystal clear. Okay. So we have two independent variables. One is we're going to vary the frequency of our stimulus, how fast the pulses are coming out of our little current source. The other one is the location on the body that we're putting the two electrodes. All right, so what is our dependent variable?
Sensory.
Say it again.
The sensory threshold.
This is going to be that sensory threshold. Okay, let's see, it's your finger here. We have the electrodes. Sending some electric current through your tissue. Again. And then what do we define? What's the definition of the sensory threshold?
Perceptual threshold?
But how would you define it? If I'm just
The lowest amount that it takes for a current.
it's going to be the lowest possible value of this electrical current that you just barely notice, you just barely feel. So it's a value. What's it measured in?
Milliamps?
Milliamps, exactly. It's like, what is the value of in milliamps that we have to push through the skin to just barely feel it? So this is important. Some of the ways people got confused in their pre-labs, they would talk about the finger having like, getting their threshold faster. It doesn't, if you're going to compare thresholds, it's not about speed or timing or anything. Thresholds are either more milliamps or less milliamps. It's just a number that's either bigger or smaller. So if you're going to compare the threshold in one condition versus another, you would say there's a larger threshold or a lower threshold, but you wouldn't like reach a threshold faster. That doesn't really mean anything. Right? So it's an actual value, a magnitude of the electrical current that you have to set this little current source to just barely feel this little twinge on your finger or your calf. So does that make sense? All right, so then we get to the objective. I am going to say at this point, I am going to start taking points off if people write objectives that are not a question. Because we've talked about it for like almost like a month and a half now. It should be a question, and it should just be a question about the relationship between the independent and dependent variables. That if that's not making sense to you, or you're reading that and it's like, oh, well, what is it? It's like, please come to office hours or let's work on it. Because there are still some people that consistently don't seem to have, obviously the word objective can be many things in different contexts, but in the context of what we're doing, I'm creating a very, very limited, like a very specific version of how I want the objective to be stated, in order to make it just easy to get at what I'm looking at, which is, I want you to be asking I'm not interested, like what is the value of the sensory threshold? We don't have enough information to figure out or to measure the value. That's going to be part of our process, is measuring a value. But what I really want to know is, like, what is the relationship between these different variables that I'm measuring, and what do I expect it to, for the hypothesis I would kind of predict. So what is the objective, given that we've just defined our independent variables and our dependent variable?
Will the frequency and different locations change the threshold?
Well, or even if you'd say, you could say, what is the effect, right? What is the, and if you could say it in one sentence like that, although in some people's sentences, it was a little tricky to know exactly if they were confusing things or not. So you could even say it's two sentences. What is the effect of, body location on that perceptual threshold? And what is the effect of the frequency of the stimulus on that threshold? And I should say question marks should have a question mark after them, or questions should have a question mark. If you write your objective and there's no question mark there, then ask yourself, like, okay, why isn't there a question mark? There should be a question mark. So, and again, in any scientific endeavor, the more clearly and concisely you can, like, ask, what am I actually doing here? What is my desired outcome? Like, this isn't just in science, this is like in life. I love this term, desired outcome. If you like walk into some meeting, before you walk into that meeting, you should be thinking about, what is my desired outcome? Why am I even doing this? What would I consider it being actually successful? In this scientific endeavor, like, what is my desired outcome? I want to find out the relationship between the location on the body and the sensory threshold. And then everything is going to be in service of trying to answer that question. Then hypotheses. There's going to be actually two hypotheses here, right? Because we have to have one hypothesis for the relationship between body location and threshold, and another for the relationship between frequency and threshold. What are compelling hypotheses for this one? This lab.
I put the greater the frequency, the lower the threshold will be because of temporal summation. And then I put the threshold will be lower on your finger than on your calf because you have more receptors in your finger than in your calf.
Right, so both of those sound pretty good, right? We talked about temporal summation. Like, if there is, let's say this is like some excitation. And here we look at the membrane voltage that goes up when you excite it, and then it drops back down. And if you excite it again, it'll go up and then it'll go down. But if you excite it, and then you excite it before it has a chance to return back to this resting, you can start stacking them. So if you start exciting this in quick succession, you can start having a cumulative effect. That's what we call temporal summation. Temporal means within in time. If you are stimulating this thing in quick succession, they're going to start stacking. So it kind of makes sense. If I am even doing it in quicker succession, they're going to probably have a chance to even stack even higher with even less of an initial pulse. So you can see that even if if I excite this thing, I change the membrane voltage, maybe this is not enough to create a disturbance in your nervous system that you actually feel. But if I have the same little pulse, but starting to do this temporal summation, the overall effect in the membrane is going to be higher, and it will hit some threshold that I'm going to feel. So again, the other thing with the body location, if I have a place like the finger where I have lots and lots of receptors and nerves, I probably don't need as much of a current going through here to get at least some part of this population over threshold and feeling something. Whereas if I'm in my calf, where there is not that many receptors at all, I'm much less likely to have something get triggered that's going to send a message to my brain that I'm going to feel as a twitch on my skin. Again, I know in Bio 110, you do the thing with the little calipers and you realize that you're just way more sensitive on your fingers than on your back of your leg, because there's just way more receptors in your fingers than in the back of the leg. So are there questions about objective and hypothesis? That's cool. Now, Sienna looks kind of like Ziggy Stardust with that.
I do have a question. I'm getting confused why the measure of the threshold would be the amps rather than the hertz.
Right, because the hertz don't tell you anything about threshold. Hertz are just going to be a quality of the signal. We have this thing here, and we turn it, it's going to actually have two different adjustments. You can adjust the milliamps, and you can adjust that, and you can adjust the hertz and tell that what it is.
But I thought we were just adjusting the hertz. Is that not right? We're adjusting the amps too?
How are we going to find? How do we actually
No.
measure the threshold?
By adjusting the amps, I guess.
Right. So we start.
Okay.
So let's say this goes onto your finger or whatever. Whatever I set this hertz to, let's say I set it to 2 hertz. As soon as I turn this thing on, it's going to be coming out, 2 per second. So if I have this set at 2 hertz and I tell this go, it's going to be spitting out bzz, 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 2 per second. How big is it? How many milliamps? It depends what I put in here. So if I'm going to find the threshold, let's say I want to find the threshold when the hertz is set to 2 hertz. What's going to be my process? It's in the lab procedure.
Adjusting the amps.
So I'm going to start, and where do I want to start in terms of my milliamps?
Really low. I forget what the actual number is. It's like 2 or something.
And how do I know for sure that it's the right value?
Because there's a minor perceptual recognition of it. No.
Now, if I'm going to find the threshold, then I better be below so I can know when I just barely feel it.
Okay.
So let's say I set this for 2 milliamps, so it's coming out at 2 milliamps into my skin. I don't feel it. Okay, that means I am below the perceptual threshold. This number 2 is too low. 2 milliamps is not it. So let's pump it up. Let's go to 4 milliamps. Now I'm sending again, it's still 2 hertz, 2 pulses per second, but a larger magnitude of milliamps. Do you feel that? Nope, still don't feel it. Nothing. All right, we're still below the threshold. All right, let's crank her up. Let's go to 6 milliamps now. Boom, boom. So now it's still 2 hertz. It's still coming out toot, 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 toot. But now they're 6 milliamps high. And it's like, ooh, I felt that. That value, what was the lowest value as you are cranking it up that you just barely feel? That is going to be the threshold, at our 2 hertz setting.
But then we go on to adjust the frequency, right?
Right. So then let's say I want to know what is the threshold going to be at 5 hertz. So I'm going to set this to 5 hertz now. So when I turn this thing on, it's now coming out way much faster. Going into my skin. But I still now have my control over the milliamps as well. So if I want to find what is the threshold at 5 hertz, I'm going to start again. And what am I going to start at for my milliamps?
Below whatever the threshold was the first time.
It's going to be below whatever. So it's probably going to be lower than at 2 hertz because we know that temporal summation. So let's start at 2 again. Whoop. So we could set it at 2. Oops. Let's put the milliamps at 2 milliamps. And now it's much faster though. Z, 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 z. Do you feel it? Nope. All right, let's go up to 4 milliamps and turn that on. That's now going to be larger, but it's just as fast as, oh, I felt that. It's like, aha, for 5 hertz, 4 milliamps is now my threshold because that's the minimum value of current that I just barely feel. So is that making it more clear?
Yeah, I got it now. Thank you.
So I find this experiment is confusing kind of in the same way that the enzyme experiment is confusing, in that our dependent variable is not directly measured. To find that sensory threshold is a process. You have to start at some milliamp less than you can feel and start slowly raising it up. Did you feel that one? Nope. Okay, raise it up a little more. Did you feel that? No. And finally, when you just feel it, that's the number you write down as the threshold under that condition. So that makes sense? All right. It also means, like, in your lab book, sometimes people get this idea they're going to do a chart, like, milliamps. Let's say this is single stimulus. This is milliamps and felt. And they do some ridiculous kind of thing like 2 milliamps, nope. 3 milliamps, no. 4 milliamps, no. 5 milliamps, no. 6 milliamps, yes. It's like, there's no reason to write that all out, right? Because I don't care. If 6 was yes, I know that you didn't feel it below. That's by definition what that yes means as a threshold. So when you're making your chart, it would be something more like this. Like, this is like finger, frequency. Frequency could either be single, which is no frequency, or it could be 1 hertz or 2 hertz or 5 hertz. I don't remember exactly what they are, 10 hertz. And here's the threshold in milliamps. All you need to do is do that process where you are starting low and going up till you barely feel it. But once you get that thing, it's like, oh, this is going to be, what did we figure? This was 6 milliamps. This is 4 milliamps. You just have to once you get the number, you can just put it in your, in the data chart. You don't have to think about like, didn't feel it at 1, didn't feel it at 2 milliamps. So your data is going to look like this. There's going to be a chart for the finger. There's going to be a chart for the calf. So is this any questions about how we get the data like that?
If we're not doing the actual experiment, how are we figuring out the threshold?
So we actually are going to take some data from a video all together in a little bit. And then the rest of the data I'll give you as a spreadsheet to complete your analysis. So we
Okay.
actually are going to, you'll get to see Tina and I doing this in lab back during the pandemic. No, I guess we're still in the pandemic. I keep wanting to think we're done. Sources of variability. Particularly on this experiment, it's really important to think about this ahead of time so you don't totally contaminate all of your data, because there's quite a few sources of variability and things that we can control for. What are sources of variability on this one?
How sensitive your hands are, like if you use them a lot, like they can be like less sensitive.
Right. So one of the nice, and in general, not even, different people have different levels of sensitivity. So we're going to have what's called like a within subject control for that. Meaning we can take readings at 1 hertz, at 2 hertz, at 5 hertz, at 10 hertz, all on the same person. So even if this person happens to be more highly sensitive or less sensitive, we can still see, well, how within that person, how is frequency affecting their threshold? Or let's look at their finger versus their calf. And maybe they're much more sensitive than somebody else, but we'll still get to compare different body locations on that person. So this is something that's actually very common, is to do like this within subject control. Like get the different conditions on the same person. So then it doesn't matter if that particular person is more or less sensitive, because we are controlling for that by just getting all the different conditions on that same person. So that's a good one. What's another source of variability?
A person's ability to sustain their attention.
Yeah, exactly. Sustaining attention. Especially you're trying to find this really slight thing, and mind wandering, that's actually, there's a lot of research these days on mind wandering. It happens pretty quick. Even if you're trying to stay focused, before you know it, you're not staying focused on things. What could we do to control for mind wandering and make sure that they're actually paying attention to feel this thing when you're actually giving them the stimulus? Think about just how you design this protocol.
You could just say, I'm going to give you a stimulus now.
Yeah, so you're gonna tell them, get ready, pay attention. Then you also have to be careful though, because if you say, I'm going to give it to you right now, they might just expect it at that moment and just feel it because, I think I felt it. So you want to make sure you don't have too much of a clue exactly when it's coming. So usually in this kind of experiment, you give them like a window, like get ready. Give them a window that's not too long, maybe 5 or 10 seconds, something that they actually can sustain their attention. but not so long that they're going to get bored, but not also instant. So it's like now, it's like, so there's a little bit of a wiggle room. So we're going to want to do some kind of a, get ready, and it's going to be coming soon, but you don't know exactly when, but soon enough that you're not going to lose attention. So that's going to be important. Able to sustain attention, we build that into our protocol by giving them a window when the stimulus is delivered. We'll see this in some other experiments we'll be doing later in the semester as well, where you want someone to pay attention, but you don't want to tell them exactly when the stimulus happens, but you also don't want them to be mind wandering. What other sources of variability do we got to think about?
The presence of sweat on your skin versus how dry your skin is.
So that could make a difference if, depending on how we were delivering the electrical stimulus. Yeah, because obviously salt water conducts electricity way better than dry skin. In fact, those lie detectors, electrodermal, like electrical activity things, your sympathetic nervous system makes you sweat, and the more you sweat, the more electricity goes through your fingers, and you can measure that really easy. You can actually just hook somebody up. It's also called GSR, galvanic skin response, and you can just watch the electrical conductivity of their hands just go up as soon as you like ask them an embarrassing question or you kick them or something. So we want to control for that, because that would be an issue. The way we're going to do that is by the way we actually deliver the electricity. So voltage is basically like electrical pressure. We've talked about electricity and voltage a bit. I'll talk in a little more. You can think of this as kind of electrical pressure. Current is like the electrical flow. Resistance is a resistance to flow. It's useful to think of the analogy of water through a pipe. The higher the the higher the voltage, the more electrical charge is going to be flowing. The less the voltage, the less flow, because it's less pressure. Resistance is going to impede the flow under any conditions. So that sweating is changing resistance. Resistance is going up and down. So if we are looking at current is going to be V over R, voltage over resistance. Like the more voltage, the more current, although the higher the resistance, that's going to be inversely. So if we just are using a voltage across the skin, then the resistance of the skin based on how sweaty you are actually is going to affect the current quite a bit, and that's going to be a problem. That would be a voltage source though, and we're not going to use a voltage source. We're going to use an actual current source. So the system we're using connects up to your skin. And we can set it, we say 2 milliamps. It will automatically adjust. It will adjust whatever voltage it needs. So that is the current going through your skin. If you're more sweaty, it's not going to need to use as much voltage. If you're less sweaty, it's going to have to crank it higher, but that's invisible to you. You don't notice that. All you as the experimenter know is you told the current to put through your subject and it did it. So by using this current source, we are able to deal with the source of variability that would be, sweat and things that change the resistance of your skin. What are other sources of variability?
Would injuries or like nerve damage be a source of variability?
Yeah, absolutely. absolutely. So this is where you'd want to talk to your subject and make sure that they don't have major nerve damage that's going to affect their ability to be a good subject for this. Anytime you do any kind of experiment, you always have to think about what are things like that, and interview your patients, your subjects, and decide whether or not there's always what we call exclusionary criteria. You have to decide before you start the experiment what qualities would make this person not a viable subject for your experiment. So some kind of neuropathy or something that affects their ability to feel, and is definitely going to make them a bad subject for this experiment. So what other sources of variability?
We're using physical hardware in this, so all of that, the computer and the software
Yeah,
and the electrode machine.
yeah, kind of the calibration and all that. Just because you turn this thing on and tell it 2 hertz at 4 milliamps, it might be lying to you. In fact, I can say when I first got hired on at the school, we used this really old equipment, and we were doing a similar experiment and getting results that really didn't make sense. And I'm like, what the heck's going on here? And I went and I double checked this really old equipment with little electrical components that had all been aging, like things like capacitors and things like that. They lose their values over time. And so I actually checked, and the actual frequencies coming out of these things was completely off from what it said on the dials. So this idea of double checking, calibrating your equipment, fairly regularly to make sure that it actually is doing what you think it's doing. It's like your stove. Like if you start, making your cakes and they're just getting burnt, what the heck is going on? And you realize, oh, the temperature is off. It's actually cooking my cake at 500 degrees instead of 350 or something. That's what's wrong, is that dial, even though I set my stove to 350, that's not what it was inside the oven. So that's the same thing happens with science as well. The dials are no longer actually indicative of what's actually being delivered. So that's always something to double check. Calibrate your equipment. What other things?
Maybe how much of the paste you use?
So that would be, having a good electrical connection for sure as well. That would make a difference. So following the procedure well. Obviously, if you don't connect the electrode to the skin, that's not going to work. Now, I'll say one more thing I will say is, whenever you are working right at the limits of perception like this, you have a lot of problems with false positives. Right, you're trying to decide, is it there, is it not there? It turns out, your nervous system has noise in it. If you have like your stereo or something, I don't know if people still have stereos, or it used to be if you had a stereo and maybe, and it's I'll make it even older, it's connected to your turntable or your CD player. I don't think any of those exist anymore. If there's nothing playing, but you turn the volume up as much as you can, typically you hear this kind of some white noise, because this thing has, just in the electrical circuitry, there is some noise. So if you turn the volume up as much as you can, you actually start hearing some of that noise that normally you don't hear because it's totally underneath all of whatever. If you're actually playing music, the music is so much louder than the noise that's within the system, you don't even notice it. But the fact is, if there is this noise that's in there, and in your nervous system, there's noise. There is in your brain, little things are zipping and zapping. And when you are trying to pay attention to just barely notice something, it's kind of like turning the volume way up to notice, like, is there a signal or not a signal? In which case, sometimes some little random noise can be perceived as like, I think I noticed something, but it was just like some little blip in your nervous system that wasn't actually anything. So it's actually not uncommon to notice something if there's nothing there, especially when you are trying to just barely detect something that's barely detectable. So it's not uncommon for somebody like, yeah, I felt that when there was nothing. So how do you get around that?
We do it more than once, like if
So
we think
you want to
they felt
double
it,
check.
yeah.
Double check. If they felt it, go a little higher and make sure they still feel it. Or give them a stimulus or pretend you're giving them a stimulus and see if they feel it. That's one thing we're not going to be able to see in real life because we're in Zoom, but it's hilarious. It very often happens within the class, even within like 20 people are doing the experiment, where there are people that totally feel it when all you did was click the mouse on a random place on the screen, that there wasn't actually anything being delivered to their fingers, but they're so ready to feel something that they're pretty sure they felt it. The same thing when we do 2-point discrimination on the skin. Again, it's kind of what you've done in the Bio 110 that we will do in this class as well, where you just take two little needles, and does this feel like 2 or 1? And as you start getting to that sensory threshold, especially like on the face, you'll feel people will say, oh, I feel it, even when they're only like a few millimeters apart. And then you say like, okay, how many is this, 1 or 2? It's like, no, I definitely feel 2. It's like, all right, so we gotta, you're not, this, we have to be careful here. So you have, this is the kind of thing I'm talking about. It's not just in perceptual thresholds with little electrical things on your fingers. It's going to be, we're going to have the same problem when we do perceptual threshold with 2-point discrimination on your skin. What's the smallest distance that you can make these two things go and know that it's 2 rather than just 1? So, you guys aren't going to have to worry about this as much because of you're not doing it for real. But if we were doing it for real, you would definitely have to worry about it. And you do have to worry about it when you do this 2-point discrimination thing at home. You're going to be doing this, just like with paper clips on like your roommate or your dog or your kids or whatever. And just because they say, I feel 2 instead of 1, don't trust them. You want to double check that. If you just put 1 down, do they still feel 2? And they might. Okay. So what we're going to do now is actually kind of all together get some initial data so you can see how that goes. And before I do that, I want to make a few more comments about the write-ups, because I've been starting to grade more of the write-ups. It's hopefully I'm going to finish them soon. I also, again, if I am going to start creating more firm due dates, because some people are just literally like 3 weeks and just not revising things, and then trying to do the full write-up, but then never actually having got the pre-labs approved. So the whole rest of the write-up is based on faulty assumptions. So then it's just a mess. So yeah, so please try to keep up on these. And like with these, today's pre-lab was nice. Almost everybody turned that in. If I gave you feedback, especially after we've just gone through all this, do what you need to do to pretty it up.
12 p.m.
And that way you also know that when you write up the nerve stimulation lab, that you're on solid footing, right? If you start trying to write up the complete lab, when you're still not exactly sure what the independent and dependent variables are, it's going to be a train wreck. Okay, so write-ups. Make sure they have methods. Some people were turning in their write-ups without having the methods in there. That has to be in there. Again, it's in that lab notebook or the lab manual. It tells about all the parts of a lab. It needs to have methods. Data, with the graphs are numbered. You can't have a graph that's just kind of an orphan. A graph has to be numbered and it has to be mentioned in the discussion.
Do does like the other data need to be numbered? Like if we do a chart, or just the graphs need to be labeled?
Kind of raw data might not be as important. Anything anything you're referring to in your discussion, you want to have like a figure number or a table number, so you can refer to it. It's a way to integrate your data with what you're writing. As we see in figure 3, there was a negative correlation between the sensory threshold and the frequency of stimulus, blah, blah, blah. So it allows you to actually use your graphs and other data to support what you're saying in the discussion. So they have to be kind of integrated with each other. Methods. Name, especially because it's just this weird COVID time. Please put your name on the top of each page. That way it makes me more comfortable that you're not taking snapshots of some friend's lab or something. It seems silly, but this past year there's been a lot of cheating, which is frustrating for me. And it means people end up not learning the stuff that they're actually supposed to be learning when they come out of the class. So it's just one of those things, just to make it feel that that it's in your book. The last thing I'll mention is your lab notebook is supposed to be all one piece, not pieces of paper stapled in. There's a few people who've kind of started thinking about stapling papers in, and I keep trying to tell from the very beginning of the semester, I was saying, don't do that. If you let's say you're in your lab notebook and here you've already written something else, and here you're like writing and realize like, oh my God, I have something else here, but I actually need to write more here, but there's no room. You don't have to staple anything in. What you can, let's say this was page 3 and this was page 4. Go someplace further in the book where there's nothing yet. Open it up to where it's, I don't know, maybe it's page 50. There's nothing there yet. And you put a big star here and say, continued discussion on page 50. And on here you say continued from page 3 and continue. That way you don't have to staple papers in there. It makes it a little funny. You have to jump from place to place, but I'd rather that than having stapled papers. And that also means that everything is still just in that same book. So please, no stapled. Okay, 12:04, we can do this. Let's do this. In fact, what I would ask you to do right now is get out your lab notebook. We can just do this together. In your lab notebook, wherever you are for this lab, it does make sure you leave room to paste in the methods and everything and background information from the lab manual. Some people, I think in general, it actually kind of makes sense to, as you're doing your objective and hypothesis, have the intro and first, but however, you're going to have whatever all this stuff, and then it's going to be time to get your data. And for the data that we're going to be doing together is in the fingers. So what I would like everybody to do is kind of get ready to record data. It's going to be from me, but it's going to be something we're going to just watch together. And what you're going to want to do is make some kind of a chart, right? It's going to be the frequency and the threshold. And again, the units for frequency are going to be hertz. Units for threshold are going to be
Milliamp.
milliamps. It's how many milliamps. That's just going to be frequency. The first one isn't actually a real one. It's just a single. Then it's going to be like 1 hertz, 2 hertz. You're just going to want to have a little chart.
Do you want us to paste in the initial information from the lab?
What do you mean the initial information?
Like before the steps and procedure, there's like background information.
Oh yeah, so I've mentioned before that that's a good idea to put that in there because it's allowed and it gives you background information, and especially given that you get to use your lab notebook on your lab exam, it doesn't hurt to have that extra information in there for you. So I would recommend putting it in.
Okay, thank you.
Okay. Well, there's some. Here we go. Share screen. Oh. Okay, so in the modules, going down, nerve stimulation lab, doing the nerve stimulation lab. All right, so it's 12 minutes. Yeah, we're gonna just make it through here. This is nerve stimulation lab starring me and Tina. Here we go. All right, so I'm gonna be the subject. Here are the electrodes. This is the little bar electrode. I'm gonna get our little conductive gel to make sure there's a good connection between the electrode and my skin. And just like kind of half of a split pea or something. You don't want too much that's going to goop everything up, but you want to make sure there's enough so there's a very positive contact between the electrode and your finger, and also it holds it on well. When you do the calf, we actually have little Velcro straps to make sure that the electrode is also firmly pulled against your calf. But for your finger, that gel works great. One of the things, source of variability with finding these sensory thresholds is the fact that you're turning up the volume so high in your nervous system, trying to detect, is there something there or not? That sometimes just the overall noise inside your nervous system might be detected as something real, when in fact it's just this, any kind of, if you take your stereo and you just turn the volume up as high as you can go, even if there's nothing on the stereo, you'll still like the white noise. Your nervous system's got noise in it as well. And when you are just bringing up the volume, trying to detect, is there just something there? It's pretty common to have these false positives. Like, I think I felt something. And in fact, there wasn't anything at all. So we need to be careful of that. One way we can do that is making sure I'm not expecting something. So I'm not looking at the screen. I don't know exactly when she is gonna turn the stimulus on.
And I'm gonna do some decoy clicking too.
But it's pretty funny when people feel things when there's nothing there, but it's actually just normal.
All right.
Also means when I feel it, she can check a little higher, make sure I still feel it. Or again, decoy clicking. She's not actually giving me any real voltage or current, but see, maybe I'll feel it anyway.
So we're going to start off with a single stimulus. So I have the monitor set at 1 milliamp, and the max repeat rate is 0.1 hertz, which means that it's going to send out 1 impulse per 10 seconds. So, of course.
Right. So this system doesn't actually let you do a single pulse. So instead, we set it to 0.1 hertz, which means 1 pulse every 10 seconds. So as long as you turn it off before 10 seconds is up, it's the same thing as a single pulse. So that's just one of the practical natures or practical things. So this first thing is basically a single pulse.
Of course, I don't want him to hear me go click on. And so first I'll just kind of click outside the box, and then eventually I'll click on, and we'll see if he feels it.
I mean, I say another source of variability is just mind wandering. So, even if there's something you might notice and you're just thinking about something else, you might not notice it actually because you're thinking of something else, your attention's someplace else. So you probably want to give your subject a window, like, kind of get ready, like in the next 5 seconds, it's going to happen. I don't know exactly when, so I can't just say, oh, that click must have been something, but you want to give your subject a heads up that in the near future, something's going to happen, if it's going to happen.
All right, so you didn't feel anything, right?
I did not.
So then I'm going to crank it up 0.2 and milliamps. And then we're going to say, so we're going to get ready to start soon. So you let me know if you feel anything, David.
I did feel something there, actually.
All right, so 1.2 milliamps is what I'm going to write down in my notebook for this, for the single stimulus for the finger. All right, and then as we move on to the multiple stimulus, we're going to subtract 0.6 from this number as a starting point. So we make sure that he doesn't feel it. You want to add anything?
Yeah, so we are trying to speed this up for you all so you're not getting bored watching us just sit around and wait. But in reality, if we're going to control for temporal summation, we want to make sure that we don't give one stimulus too quick following a previous stimulus. So when you're doing this experiment for real, you want to wait at least 30 seconds after you give an initial stimulus. If they don't feel it, you just get to sit around for 30 seconds before you go at the next level up. So it ends up being this is a lab where people often finally get to know each other and get to know more about each other's lives, because there's a lot of time to kind of sit around while you're waiting in between each stimulus. But does that make sense? Why you don't want it? right? Because if you just like feel that, oh no, feel that, no, feel that, no, feel that, you're actually going to start doing temporal summation without meaning to. And that's going to be a confounding factor. So by waiting 30 seconds, you make sure that the system kind of restabilizes before you do the next level. And again, it's one of this, it is literally a lot of waiting around, and it is really kind of fun to watch people just get to know each other. But unfortunately, next semester, students will experience that again. Maybe.
Right. So since we're moving on to multiple stimulation and we're going to change the hertz. So this time I'm moving it to 1.0. And if you have any trouble with the decimal point, you can just use the keyboard on the numbers here and type it in. Sometimes it wants to do something that you don't want to do. And so right now I just typed in 1.0. So hertz, 1.0 hertz, and now I'm going to subtract 0.6. So since his last trial, we wrote down 1.2, it's going to be 0.6 that we're starting.
For the milliamps.
Yes. All right, so are you ready to start?
I am ready.
All right, let's start. Let's see. Nothing?
Nothing.
All right, so now I'm going to add 0.2. So I'm going to change that to 0.8 milliamps. Are you ready to start?
I'm ready.
And we didn't feel anything, so we change that, right? All right. So next one is going to be 1.0 milliamps. And are you ready to start? Can you even feel anything?
I don't think so. I mean, it's kind of funny. It's like I kind of feel some tingling, but even when nothing's happening, I kind of feel my finger.
All
So
right, so
I
maybe
don't-
we'll crank up one
Yeah,
more and check,
yeah.
and then we can always go back and check it
Yeah.
out. All right, so I'm gonna up it to 1.2. And are you ready?
Mhm. No,
Maybe.
I say yeah, but I keep going up because
Alright.
it's not definitive.
All right, so we're gonna up it to 1.4. All right, are you ready?
I found something.
All right, so definitely 1 for birdie. I'm gonna go back to 1.2 and see if you think. Ready?
So there, I do feel something there.
All right,
Yeah, because it's, but you feel it kind of goes, z. It's not as.
so
Yeah.
we'll write down
Yeah.
1.2 in our
Yeah.
notebook for that.
Yeah, no, that's. Right, so, yeah, and I found those cool little sparkles that I added into the video. So the sparkles mean I felt it. The thing to remember, 1 hertz is different than single, right? Keep it, especially if you're not as used to the idea of hertz, right? 1 hertz is repetitive, 1 per second. Boop, 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 boop. Single, it just happened once and nothing else. So here for 1 hertz, I've got 1.2 milliamps. Now we're going to continue. It's interesting because I wasn't sure whether it was just my finger feeling all vibrating, but it was actually,
Okay.
once I really thought about, oh, 1 hertz, it is coming like that.
All right.
Cool.
All right. So next is we're gonna up the hertz to 5 hertz, and then we're gonna subtract 0.6 from 1.2. So we're gonna start kind of where we started last time, 0.6. You ready?
Mhm.
All right. Nothing? So I'm gonna up it. And normally you would wait 30 seconds between these trials. So we're trying 0.8. Are you ready? Mhm. Nothing. So we're up it to 1.2. All right, you ready?
I do feel some tingling in there.
All right, so then we will record 1.0 milliamps for the 5 hertz, and then we up it to 10 hertz. And we're going to subtract 0.6 from the 1, and so we need 0.4. All right, so you're ready? Okay. Nothing. All right, so 0.6. And we'll start. Nothing. Nothing. Go to 0.8. Nothing. No. All right. We'll go for 1.0. Start.
Oh, that's definitely a tingling there.
All right, so we'll record 1.0, and then we're gonna up the hertz to 25 hertz. And we're gonna subtract 0.6 from the 1, so we're down to 0.4. That's our starting. So you ready? All right. Nothing?
Nothing.
All right. Up to 0.6. Start. Okay. Up to 0.8. Nothing. All right, and maybe 1.
Yes, I definitely feel something there.
All right, so we will record 1.0 for the last on the fingers. All right.
And then obviously any one individual subject has their data, but to really look for overall trends, you have to kind of average across many subjects, and you'll be getting a spreadsheet with the results from many subjects and look at, on average, what do we find? You know, it's interesting to look at an individual, but that's never going to tell you like the complete story.
All right.
All right. So that was, so any question just about the process? Partly we wanted you to kind of go through this, you know, just to really understand what it is, what it meant to get the threshold, how it was this multiple step process. So you can really see what it means to have, what that dependent variable is and what that process looks like. So like in your lab notebook, I would like you to have that data as if like it's your data that you can then like kind of compare to the overall class data. But we do have the overall class data right here, which is right below the video, which you are then going to also include as part of your write-up. So you're going to have to, so let's, so this will be part of your write-up. You know, here are all the different subjects, and here's the average between the different subjects. So again, what is the first part of our, what's somebody's hypothesis for like location versus threshold?
You'd have a lower threshold on your finger than on your calf.
And if we take a look here, it's like, oh my God. Basically the threshold, we needed only like half as much current to feel it. This is like just for the single, but as we'll see that, if you look at the data, basically whatever frequency you're looking at, it's always lower on the fingers than on the calf for any kind of condition. So that's nice. That's supporting that part of the hypothesis. What was the other part of the hypothesis?
The higher the frequency, the lower the threshold.
Yeah, so like we can look on the finger and we can see like, oh my God, as frequency goes up, threshold becomes less. You can use a smaller value of the milliamps at the higher frequency and use to feel it. If we look on the calf, the same thing. Well, it doesn't matter if we're looking at the finger or the calf. And again, what do we call this kind of a relationship where one gets smaller as the other gets bigger?
Inverse.
It's inverse relationship, right? As the frequency goes up, the threshold goes down. It becomes lower. So again, we can see both on the fingers and on the calf, this really nice inverse relationship between frequency of the stimulus and the value of the perceptual threshold. And again, looking at body parts, we see also a very clear result here. So, in your write-up for this one, at this point, hopefully you'll have, I would say I will do my best, like even before I go to bed tonight, to give you feedback on your pre-labs, but make sure your pre-lab is correct before you do the rest of your analysis, because like I said, it is just going to be a train wreck if you try to do the more elaborate analysis when you don't have a firm grounding on the foundation. So, and it's 12:27, so we are actually ahead of schedule here. We don't, usually I go a little over, but today I'm like kind of done 3 minutes before it's done.
I have a quick question. For the calf data, are we just using the class data for that, or is there another video that we need to watch, like what we just did?
No, that would be painful for you guys.
Okay.
We wanted you to kind of go through the process to really understand how we were getting the data, but beyond that, it just seems kind of gratuitous.
Okay, thank you.
Yeah. Any other comments or questions about this stuff?
For the data that we just got, should we consider that figure 1?
Yeah, that would be good. That would be figure 1, sure.
Thank you.
So then, and then you can talk about, how does that data relate? Is it consistent with the overall class data? Otherwise, so I will be here, but yeah, and actually for the next few labs, there are no pre-labs. So we'll just, you should read ahead so you got an idea of what we're up to, but you don't have to prepare anything in advance. So yeah, we'll, over the next few classes, we'll do these sensory labs, the general sensation and the hearing and the vision and the taste and stuff like that, which will make more sense because we'll be doing that in lecture as well. So I will see you all on Thursday.